Welcome to The Explainer. So today, we're going to tackle one of the most famous and honestly most misunderstood rules in all of science. It's a number that basically decides what gets published, which drugs get approved, and in a lot of ways, what we believe to be true.
All right, let's just jump right in with this pretty provocative idea from J.H. Kim. What if the gold standard for scientific proof, this number we all learn about, isn't as solid as we think it is? What if it's just, well, a habit?
Okay, so first up, let's talk about this rule that pretty much governs so much of our research, from medicine all the way to social sciences. It's the ultimate gatekeeper that separates a real finding from a random fluke.
You know, for decades, this one little number has had so much power. We're taught that if an experiment's result has a p-value of less than 0.05, it is statistically significant. And we're told that this is like the gold standard, strong enough evidence to say that a result probably isn't just a product of random chance.
So what in the world is a p-value anyway? Well, to put it simply, think of it as a surprise meter. A low p-value, maybe something like 0.03, is basically saying that your results would be really surprising if your starting assumption that there's no real effect happening was actually true. It's kind of like an indirect clue that your initial hunch might be wrong.
Okay, but this is where things start to get a little shaky. That 0.05 threshold, it is not a law of nature. It wasn't derived from some deep, universal mathematical principle or anything like that.
So, you might be wondering, where did this magic number even come from? Well, get this. R.A. Fisher, one of the fathers of modern statistics, basically just picked it. Yep, he argued that a 1 in 20 chance seemed unusual enough to be worth paying attention to. It was just a suggestion, a rule of thumb, that somehow morphed into this unbreakable scientific law.
Now, this becomes a huge problem in our age of big data. See, with enough data points, you can find a p-value below 0.05 for almost anything. Think about it like this. With a sample size of 1,000 people, a tiny, practically meaningless connection between two things, a correlation of just 0.05, can spit out a p-value of 0.004. And by the books, that would be labeled highly significant.
This is what some researchers call an illusion of predictability. So here's the bottom line. A low p-value does not automatically mean the effect you found is important or large or even meaningful in the real world. All it really means is that it's probably not zero.
To really get why relying on this one number is so risky, we've got to talk about the two main ways an experiment can go wrong.
First up, you've got your type 1 error, the false positive. The easiest way to think about this is a fire alarm going off when there's no fire. You're concluding an effect exists when it really doesn't. And then you have the type 2 error, a false negative. Now this is way scarier. This is the fire alarm failing to go off during a real fire. You completely miss a true effect that's actually there. And get this, every single statistical test is a trade-off between these two mistakes.
And listen, these aren't just, abstract concepts for a stats class. A false positive can cause real harm. Patients might get treatments they don't need, hospitals waste precious time and money, and whole fields of science can get sent down a rabbit hole chasing something that was never there to begin with.
But a false negative? That's just as dangerous, if not more so. I mean, imagine a life-saving drug getting tossed aside because a test said it didn't work. A critical discovery could be completely overlooked just because our test wasn't sharp enough to see it. We miss a real chance to make things better. So all of this leads to a really critical question. Are these two types of errors equally bad? Well, as you're about to see, the real-world consequences are almost never the same.
Let's make this super concrete. Think about a pregnancy test. Which mistake is worse, right? Telling a pregnant person they aren't, which risks the health of both them and the baby, or telling a non-pregnant person they are, which leads to some temporary shock and confusion. I think we can all agree one of those is way, way more serious.
Right? We instinctively know that the stakes are different. For something like a pregnancy test, we want to be absolutely sure we don't miss a real pregnancy. We'd rather have a few false alarms than miss the one real thing.
And you know what's wild? This way of thinking isn't new at all. Our society already does this. I mean, just look at our legal system. It has totally different significance levels. In a civil trial, where it's usually about money, the standard is just a preponderance of evidence. Basically, a little better than a 50-50 chance. But then you get to a criminal trial, where someone's actual freedom is on the line. The standard there is beyond a reasonable doubt. That is an incredibly high bar. We are deliberately making it very, very hard to get a false positive to convict an innocent person. So it really makes you wonder, if we're this careful and thoughtful in a courtroom, why on earth aren't we doing the same thing in a research lab?
Okay, so this brings us to a much more thoughtful way to approach all of this. The goal isn't just to find some new magic number to replace 0.05. It's about adopting a mindset that's way more flexible and aware of the context.
So instead of just blindly slapping that 0.05 rule on everything, researchers should be asking a couple of key questions. First, how big is my sample size? Because if it's massive, I've got to be way stricter to avoid finding junk. And second, what's the real cost if I'm wrong? You should set your threshold to minimize the harm of the more dangerous error.
But what if we could just get rid of the whole simple yes or no answer completely? Well, some statisticians are pushing for a much bigger shift in thinking, an alternative idea known as Bayesian statistics.
Okay, I know this might look a little intense, but the main idea here is actually pretty simple. The Bayesian approach doesn't give you a hard yes or no. It's all about taking what you already believe, they call that your prior belief, and then using the new data to update that belief. It's way more intuitive, treating evidence as a spectrum, a matter of degree, instead of a simple on or off switch.
At the end of the day, it really all boils down to this one powerful idea. A loss function is just a fancy way of talking about the real-world consequences of getting it wrong. And without consciously thinking about those costs, the numbers that our fancy statistical tests spit out are, well, they're pretty much meaningless.
So the next time you're scrolling and you see some headline about a significant new scientific finding, what are you going to ask? Are you just going to accept that p-value at face value, or are you going to push a little bit? Are you going to ask about the size of the effect, the sample size, and yeah, most importantly, what was really at stake if they got it wrong?